Hello everyone. Now we are going to take up very interesting topic, that is real life application. That is, if you just see the slides, optimal cooling of stack of vertical heat generating plates. That is, if I have this portion where I need to keep, I want to stack the plates. The question is how many plates I should keep, or for given plates what is the heat transfer, maximum heat transfer I can afford to get is the question. So determination of optimal spacing so that the heat transfer rate to the ambient is maximized by natural convection. That is the question. How do we apply these basics? So the distance between the two plates, we take it as d. This is my g. These are maintained, each one of them are maintained at the same temperature Ts. The total distance between is L. Height of each plate is h. Although my figure doesn't show like that, but we are taking it as h is the same for everyone, and T infinity is my fluid temperature all around. So L by D is equal to N, number of plates, because I am assuming thickness is very small. Thickness of the plate is very small. So there are two limiting conditions which I can take up, that is D tending to 0, that is small spacing limit, and D tending to infinity, that is large spacing limit. For both the cases we have already closed form solutions. So, and it is assumed that each of the board is maintained at Ts. So known are h, w, which is width of the plate, Ts, T infinity, L. These are known. Now let us see how do we get the optimal heat transfer rate. So if we take D tending to 0 case, we have already found just in the previous module that Q dot A is equal to Q dot we found for two plates. So that is Q dot into L by D, that is number of the plates. So you can write, we just now found Q dot equal to, this was the equation we just found. So I am just going to take this directly, this solution. So you get rho Cp Wg beta Ts minus T infinity squared D cube divided by 12 nu into L by D. Please notice that as D tends to 0, that is Q dot A decreases as D squared increase. As D is going on decreasing, Q dot A also goes on decreasing, because I want to bring the plates as closer as possible. Now let us take up the D tending to infinity limit. D tending to infinity, large spacing. That means the plates are so wide enough that the boundary layer of one plate will not interfere with the boundary layer of the another plate. So we have found we will take Prandtl number greater than 1 case, and delta T for Prandtl number greater than 1 case is h RAH to the power of minus 1 by 4. We are saying that the D is greater than h RAH to the power of minus 1 by 4, so that they are not interfering. And the Rayleigh number, to remind you, is G beta Ts minus T infinity h cube upon alpha nu. Now how many boundary layers will be there? For each plate there will be 2 boundary layers. So you will have 2 into L by D. So Q dot B is equal to 2 into L by D and QBL, that is heat transfer by the boundary layer for the each plate. So now QBL is equal to HH bar, that is the average heat transfer coefficient, over the complete vertical plate, and W into H, heat transfer coefficient, into area into Ts minus T infinity. So we know that Nusselt number NuH equal to, for a vertical plate, 0.59 RAH to the power of 1 by 4. I am considering this as laminar boundary layer. That is Rayleigh number 10 to the power of 4 to 10 to the power of 9 I take. So QBL, so that is HH bar equal to K by H into 0.59 RAH to the power of 1 by 4, because NuH equal to HH by K. So substituting this, you get QBL equal to K by H into 0.59 into Rayleigh number to the power of 1 by 4 into W into H into Ts minus T infinity. Now if you substitute this in Q dot B equal to 2 into L by D into K by H into 0.59 Rayleigh number to the power of 1 by 4 W into H into Ts minus T infinity. So you see that Q dot, as D tends to infinity, that means as D increases, Q dot B increases. If you just see, Q dot B increases as D to the power of minus 1 with the increase of the D to the power of minus 1, or with the increase of the D. So now if we come back, if we plot this, whatever we have gotten, that is Q dot A and Q dot B. So this is Q dot versus D if you plot. So Q dot A, this is Q dot is proportional to D squared, that is one limit A. Another one is Q dot is of the order of D to the power of minus 1 for large spacing. This is what we got just now. Q dot is D to the power of minus 1 proportional to. So, but actually if you really solve, you will get somewhere a solution like this. So, the point at which both intersect, so Q dot A has to be equal to Q dot B. So if I equate them, so Q dot A, whatever I have gotten, if I write that, what is Q dot A is rho Cp Wg beta Ts minus T infinity whole square d cube upon 12 nu into L by D is equal to 2 into L by D into K by H into 0.59 Rayleigh number to the power of 1 by 4 into W into H into Ts minus T infinity. So you get this. So you get G beta Ts minus T infinity into d cube upon alpha nu is equal to 12. If I push into 0.59, I get 14.16 and Rayleigh number to the power of 1 by 4. Rest all are getting cancelled out, W by H, L by D, Ts minus T infinity. So this is what you get by equating. So now this is, what is this? This, if I write G beta Ts minus T infinity into H cube upon alpha nu into D by H whole cube, I can write, I have just multiplied and divided by H cube. So this is equal to 14.16 Rayleigh number to the power of 1 by 4. So whole of this combined, I get Rayleigh number. So that is Rayleigh number. So I get D optimum upon H is equal to 2.42 Rayleigh number to the power of minus 1 by 4. Actually it becomes minus 3 by 4 and I have taken cube root, so I get minus 1 by 4. 14.16 cube root is 2.142. So this is what I get. And if you substitute this D optimum either in Q dot A or in Q dot B, you are going to get Q dot B equal to 2 into L by D into K by H into 0.59 Rayleigh number to the power of 1 by 4 WH into Ts minus T infinity. If you substitute this D optimum here, you are going to get Q dot maximum equal to, if you just come to the slides, if you just substitute this 2.42 for this D optimum and do the algebra, you are going to get 0.49 K into Ts minus T infinity into LW by H into Rayleigh number to the power of half. You see the power? We just D tending to 0 and D tending to infinity, and we could get the optimal solution. This has been solved numerically also and has been found that closely these coefficients are closely correct within 5 to 10%. That is anyway is going to be there. Even when you do the experiments, that kind of uncertainty is going to be there. So that's about the optimal cooling of the stack of vertical heat plates. Now only one thing which is going to be little we have not done is uniform heat flux. We have done so far for constant wall temperature. If you just see the slides, see Q double dash constant we come across for radiation heating from one side, electronic components, nuclear radiation heating, they all constitute constant heat flux boundary condition. So that is Q dot double dash is of the order of K del T by del T. This is the scale. That is, if we have to understand, if you just take vertical plate, this is Y and this is my boundary layer. So flow is in this direction. So you can see that delta T, this is my delta T is of the order of Y to the power of 1 by 4, H RAH to the power of minus 1 by 4. That means it is H to the power of 1 by 4. Okay. So you get, see, delta T is of the order of H to the power of 1, H cube. You see H cube is there, minus 3 by 4 plus 1, that is you get 1 by 4. So delta T is of the order of Y to the power of 1 by 4. Now the heat flux, what would be the heat flux? How does the heat flux vary for the constant wall temperature? I am showing for the constant wall temperature. So this is delta T. How does it vary? Q double dash is K delta T by delta T. So Y to the power of my Q double dash will vary Y to the power of minus 1 by 4. Okay, it's just the inversion. K and delta T are constant. So Q double dash is of the order of Y minus 1 by 4 and delta T is of the order of Y 1 by 4. This is for constant wall temperature. If you take uniform heat flux case, the boundary layer we are going to show now, the boundary layer delta T is of the order of Y to the power of 1 by 5 and heat flux is going to be constant. Your heat flux is going to be constant. This is heat flux and your delta T is going to be of the order of Y to the power of 1 by 5. We will show that. So let's get started. You have delta T for constant heat flux. Delta T is of the order of H RAH to the power of minus 1 by 4. That is H G beta delta T H cube upon alpha nu to the power of minus 1 by 4. So that is delta T is of the order of H into G beta. Now what is delta T? Q double dash is of the order of K delta T by delta T. So now delta T will be of the order of Q double dash delta T by K. So I will substitute for delta T this thing because I want to get heat flux instead of delta T. Q double dash delta T by K H cube upon alpha nu to the power of minus 1 by 4. Now if I pull out delta T is of the order of, okay, delta T to the power of, if I do delta T, if I just do the rearrangement, so what do I get is G beta Q double dash. What is delta T? Delta T is nothing but my H. What is delta T? So you have Q double dash, this is delta T to the power of minus 1 by 4. If I pull this side, it becomes plus 1 by 4. 1 plus 1 by 4, this becomes 5 by 4. So G beta Q dot double dash into H cube upon alpha nu K to the power of this is H to the power of minus 1 by 4. So if I write for delta T, because I will take the power as, so then I will have to multiply this power by 4 by 5. So H to the power of 4 by 5. So whole of this G beta Q dot double dash H cube upon alpha nu K is going to be minus 1 by 5. So I would define, so if I delta T into H into G beta Q dot double dash H to the power of 4 upon alpha nu K to the power of minus 1 by 5. I hope you got what I am doing. This is minus 4 by 5, sorry, H to the power of minus 1 by 5 plus 4 by 5, I am going to get H. So you get, so I am defining Rayleigh on the basis of constant heat flux, that is Ra star, star means constant heat flux. I am defining that as G beta Q dot double dash H to the power of 4 upon alpha nu K. Alpha nu K. So if I substitute that, so this is delta T H Ra star H to the power of minus 1 by 5. So I got my delta T. So you recollect Nusselt number, I don't have to do anything. Nusselt number is of the order of delta T by H to the power of minus 1. We have derived this several times. So Nusselt number is of the order of Ra star H to the power of 1 by 5. Remember, I have taken this for Prandtl number greater than 1. Okay, so you got, now you can see that delta T, if you just come to the slides, delta T is Q dot double dash H Ra H to the power of minus 1 by 5 by K. So H into H to the power of minus 4 by 5, that is H to the power of 1 by 5. So that is why delta T is of the order of y to the power of 1 by 5, y to the power of 1 by 5. So Nusselt number we got. Now if we write for, if you just see the slides, for Prandtl number 1, constant wall temperature, we know this. For constant wall heat flux, we just derived H Ra star H to the power of minus 5, and delta T is Q double dash H Ra star H to the power of minus 1 by 5 by H, and Nusselt number is Ra star H. So you can notice that delta T is of the order of H to the power of 1 by 5. So, and similarly you can work out, I am not working out, similarly you can work out for Prandtl number less than 1. All that it means is, wherever 1 by 4 is there, it will be replaced by 1 by 5 with the Rayleigh number definition as G beta Q double dash H to the power of 4 by alpha nu K. Okay. So with this, now we take up this Nusselt number equal to, see whether this is correct or not, that is the question. So you have for Prandtl number greater than 1, you get Nusselt number is of the order of Ra star H to the power of 1 by 5. For Prandtl number less than 1, Nusselt number you get Ra star H Prandtl number to the power of 1 by 5. Is this correct or not? Sparrow has given for constant heat flux boundary condition 2 by 360 to the power of 1 by 5 into Prandtl upon 4 by 5 plus Prandtl to the power of 1 by 5 or A star y to the power of 1 by 5. Now you see, if you take Prandtl number tending to infinity, this equation reduces to nu, infinity by infinity, this is kind of 1, so you get 0.616 or A star y to the power of 1 by 5. Okay, and Prandtl number tending to 0, so that means this is 0, 1 upon 4 by 5, sorry, Prandtl number upon 4 by 5, so you get Nusselt number equal to 0.644. 4 by 5 plus lowest Prandtl number, I can neglect this. So this Prandtl number in the numerator I can retain, Prandtl number in the denominator I can remove. So I get R A star y into Prandtl to the power of 1 by 5. So this is nothing but what we got here. This is nothing but what we got here. So what we have gotten with the simple rearrangement of the Nusselt number, what we got for constant wall temperature is working for the constant heat flux also. So this has been proved. So now I would like to show you, with this we are kind of completed with the natural convection. So now let us take up experiments. I would just show you one simple experiment how one can do with a vertical plate. So if you just take a vertical plate, so I am just going to show you a video. Just watch this video. It's 2.5 minute video. So there is a string. You have filled this container with the water, and this container with this string is kept in the refrigerator so that you can generate vertical plate. So now the ice is formed. Now we need to prepare the enclosure. Now we are ready with the vertical ice plate. That's my vertical plate. Now I drill this box so that I can insert thermometer. Why plastic box? Because I want to create an insulated chamber, so that's why I created plastic bottle, plastic not bottle, plastic container. There is a hole made. I just file it so that I can fix the funnel. I fit the funnel so that as it melts, I am going to hang this ice inside my container. Now the funnel is fitted inside the container. You see the funnel is fitted. Now I put the cork for the tight enclosure so that there is no, for putting the cork I am taking insulating material, and insulating material I am getting it cut. And then I am attaching thermometer with that insulating material so that there is no loss of heat, and I have hung the ice from the top. You can see here the ice being hung. So that is the complete apparatus. This is the complete apparatus. The hung ice, funnel, thermometer on the top, and I will take a small beaker, measuring flask at the bottom so that I can collect the melted water directly. So that is the video. Now let us see how do I do the calculations and compare my values with the, so this is my, these are my sample calculations, that is these are the properties. T infinity is 25 degrees Celsius and Ts, my ice I don't have to measure, that's why I have chosen ice is at 0 degrees Celsius. Tf equal to film temperature is Ts plus T infinity by 2, 12.5 degrees Celsius. At 12.5 degrees Celsius, all these properties alpha, nu, Cp, K, Prandtl number are put. So you get, so this is the volume you have measured in this slide. If you see this slide, you can see the volume measured 5 ml you measure, mass would be, you just multiply, mass would be kg, ml would get converted into kg by multiplying by 10 to the power of minus 3, and it has taken 342 seconds. So the mass flow rate is 1.462 into 10 to the power of minus 5 kg per second. So the Rayleigh number, how do you calculate the Rayleigh number? Rayleigh number equal to g beta Ts minus T infinity into h cube upon alpha nu. You will substitute for Ts as 0, T infinity as 25, it doesn't matter, you can flip T infinity minus Ts, Rayleigh number negative has no meaning, h height is 0.16 meters, and all the properties, if you substitute all the properties as you given here, you get 1.21089 into 10 to the power of 7, that means it is laminar. So now m dot HSF, that is melting, the latent heat of melting, should be equal to the Q dot, that is twice, because it is boundary layer is on both the sides of the vertical plate. So you have 2 into W into K into T infinity minus Ts into Nusselt number. You will not get it, so let me explain it. K into T infinity minus Ts. What is Nusselt number? H by K. So if you just see here, K gets cancelled out. So W into H, you get 2 into W into H into T infinity minus Ts. That is area into Ts, T infinity minus Ts. So that is nothing but the heat transfer rate. So only thing, I want the answer Nusselt number, so I have written like that. I have measured this m dot, so I would substitute that is 2.38 into 10 to the power of minus 5, which is what I had gotten here in my slides here. So 2.38 into 10 to the power of minus 5, and HSF is 334.4 into 10 to the power of 3, and width I know that as 0.105, and height I don't need here for this, width is 0.105. Thermal conductivity of water is 0.02503. Sorry, it's for the air, thermal conductivity is for the air, 0.02503 into T infinity minus Ts is 25, and I can calculate Nusselt number. If you just see here, you get the Nusselt number as 60.384. But taking whole of this m dot HSF is wrong, because radiation losses are there. So what is the radiation loss? Radiation loss is Q dot rad is equal to sigma epsilon T infinity to the power of 4 minus Ts to the power of 4. Epsilon is 1. Ice is having an emissivity of 1. So you don't have to bother about that. Sigma is 5.67 into 10 to the power of minus 8. T infinity is 298 and Ts is 273 because it is sitting at 0 degree Celsius. You get 4.44 watts. But actual heat is 2.38 into 10 to the power of minus 5, that is m dot, into HSF is 333.4 into 10 to the power of 3, you get 7.935 watts. So Q dot natural convection is 7.935 minus 4.44, you get 3.495. But we have taken whole of m dot HSF in my calculation. Instead of that, if I just take 3.495, I am going to get a Nusselt number of, if you just see this slide here, you are going to get, okay, 3.495 H into 2 into 0.16 into 0.105 into 25. This is the area, twice it has taken because two boundary layers. You get H equal to 4.1607. HH by K, you get 4.1607 into 0.16 upon 0.02503, you get 26.31. But if you see the correlation, empirical correlation for NuH, you get Nusselt number of 33. So this is experimentally obtained value and this is the theory. So this is kind of, I mean, I'm not saying it's very close, but this kind of proves that the way we have done the experiment is quite nearer to my theory, and 6 in 30, that is around 20% is my variation. But of course there are a lot of uncertainties, so maybe the way I have there might be some blowing of the air or something, so am I maintaining the natural convection completely better? So some uncertainties would tantamount for this variation. So much about the natural convection. With this we have covered the natural convection for laminar boundary layers, and for turbulent we have not covered, and also we have not covered the integral solutions and the similarity solutions. But with the approach what Professor Arun has taught you for the forced convection, similarly you can extend yourself for integral approach and the similarity approach for natural convection as well. Thank you.